Hello! The topic for today is maxima and minima. So we're very often interested in where a function has its peaks and where it has its lows. For example, a business person may be interested in where their profit function takes on its maximum values. Or an electrical engineer who has some sort of function that measures voltage would be interested in where the peaks in voltage are, because those are the places where it hits the equipment the hardest. In today's lesson, we're going to learn how to find these peaks, maxima, and lows, minima, using calculus. And we'll also establish conditions under which we know a function has a maximum or a minimum.
Hello, calculus students. The topic for today is maxima and minima. Looking at the graph there in blue, we can talk about the idea of local extrema and absolute extrema in a really visual way. First, let's talk about local extrema. So when we use the word extrema here, that just means a minimum or a maximum. And when we talk about local extrema, those are just either minimums or maximums in the neighborhood. They may not be overall the highest or lowest points on the graph, but just near the point in question, they're extrema. So for example, this point here, that first little hump, that's a local maximum. It's certainly not the highest point on the graph, you can see that. But just in the neighborhood of that point, it's the highest point around. So you can kind of think of local maximums and local minimums as sort of little mountaintops and valley bottoms that you might see on a graph. Over here, this point, this sort of first little trough that you see, that would be a local minimum, of course. And then there's that sharp point right here. That would be another local maximum. But again, it's not the highest point on the graph total, right? Now this point over here, when you survey all the points on the graph, it definitely is the lowest point of all. So that would be an absolute minimum. And this point on the far right over here, you can see this is the highest point on the graph. And so that would be your absolute maximum. And on the far left of the graph over there, you can see that it's actually in the region just around that point. It's the lowest point. So the far left-hand point would be a local minimum, but it's not the overall lowest point. Let's think about where might we expect to find extrema, either local or absolute, on a graph. Whenever you have those points that are sort of like smooth mountaintops, like sort of rounded off mountaintops or sort of rounded off valley bottoms, you can actually identify those places, because if you think about the derivative, you'll see that the derivative is equal to 0 at those kind of points. For example, at that first local maximum on the left, where it's a little hilltop, the derivative at that point, in other words, the slope of the tangent line, looks like this. So notice that the slope of the tangent line there is equal to 0. And you see the same behavior at the local minimum just to the right of that point. The slope is 0 there of the tangent. And even at our absolute minimum value, we see a place where the derivative seems to be about 0. At that local maximum near the middle of the graph where there's a sharp point, well, we know that when we have sharp points like corners or cusps, those are places where the derivative is undefined, because, you can't define a unique tangent line at those points, right? There's like lots of ways that you can have a tangent line there. So at those kind of places, the derivative is undefined. Sometimes it just happens that you have local extrema at the endpoints, or absolute extrema at the endpoints. So that last point on the far right where the absolute maximum occurs, it's not like really the top of a hill. I mean, the graph seems to be, if you could extend the graph past B, it seems like it was on its way upward. So it's just an endpoint, right? So it appears that, it can happen that extrema happen at endpoints. Same thing happens over here. It's a local minimum on the far right, but just because it's an endpoint, not because the graph flattens out there or something like that necessarily. So that's a pretty good survey of the sort of things that can happen where you get extrema. So let's write all that down. So where can these extrema occur? Well, we see that it can happen at endpoints of the domain. And then we saw that it could happen at interior points of the domain where the derivative is equal to 0. And then we also saw that it can happen at interior points of the domain where the derivative is simply undefined. And really, this picture that we drew is pretty representative of all the things that can happen. It turns out, in fact, though, there's a theorem that guarantees exactly what I said. So theorem 4.2 here at the very bottom of the screen, it says if you got a local maximum or a minimum at a point, and you know the derivative exists there, then the derivative must be equal to 0 there. So that allows for the possibility of, it's like, this is an if-then statement. It says if there's a local maximum and the derivative exists there, then the derivative has to be 0. But it could be a local maximum or minimum where the derivative doesn't exist. And where are the two kinds of places where the derivative doesn't exist? Well, it could be at the endpoint of the domain, because the way we define derivatives in terms of a two-sided limit, derivatives don't exist at the endpoints. Or it could just be a place in the middle, like that sharp point that we see there in the middle of that graph, where the derivative just does not exist. All three of those kinds of points that I mentioned before, you can deduce that that's what you might get from this theorem. And the kind of points listed in number 2 and 3 there, the interior points where the derivative is equal to 0 or the interior points where the derivative doesn't exist, those have a special name. They're called critical points. And so that's the topic of the definition at the bottom. It just says critical points are exactly those points that are interior in the domain, and either the derivative is equal to 0 there or the derivative just fails to exist. So those are the points that are sort of most interesting. If someone hands you a function, anybody can see what the endpoints of the domain are. Okay, so fine. You know that that's a place where you might get an absolute minimum or maximum. And so you got to find these interior points where the derivative is equal to 0 or the derivative is undefined to get these critical points. So we need to practice finding critical points. Critical points are really important if we're interested in figuring out where a function has its extrema. By the way, I didn't mention it at the beginning, but you might be wondering, why do I care where a function has a maximum or a minimum? But I think probably a moment's thought and you'll realize that, that's probably a pretty important topic. In fact, I would guess that finding extreme values of functions is one of the most important applications of calculus. There's all sorts of situations in the real world where you want to know where a function is having a maximum or where it's having a minimum. If you're into economics, you would like to know if you have a function that tells you what your costs are for manufacturing something, well, then you'd like to know when your costs are going to be minimized. Likewise, if you have a function that's telling you profit, you'd like to know when your profits are going to be maximal. And if you're doing some sort of engineering application involving voltages, you might like to know, if you got a function that measures the voltage, you might want to know where the spikes in voltage are going to be. Like what kind of parameters are going to cause a maximum voltage or minimum voltage. The list goes on of applications where you want to know minimums and maximums. And so as long as we're dealing with functions that can be differentiated, we're going to have some pretty good procedures for finding such places. So like I said, these critical points, we have to study those. We have to figure out how to find them. That's the key to all this. So let's practice on finding critical points for a moment. Finding critical points can be kind of tricky. Let's see if we can do it for some relatively simple functions, though. So in this first example, we got the function f of x equals x cubed over 3 minus 9x. I want to find all the critical points for that function. Well, first thing we have to do is find the derivative. because the critical points are based on where the derivative is equal to 0 or where the derivative is just undefined. So first task is find the derivative. So f prime of x, for this function, this shouldn't be too hard. You bring the 3 down on the first term, you get x squared, then you get minus 9. And so then you have two kinds of critical points, right? First, we're going to do values of x where f prime of x is equal to 0. So just take the derivative, which is x squared minus 9, and set it equal to 0 and solve for x. And pretty quickly you realize by adding 9 to both sides and taking square roots that x can be plus or minus the square root of 9, or in other words, plus or minus 3. Okay. And second, we have to always consider what are the values of x where that derivative is undefined. Well, in this case, it would be none, because the derivative, x squared minus 9, is a polynomial, and it's defined for all real values of x. So our list of critical points here are just -3 and +3. It might be interesting to have a look at the graph of x cubed over 3 minus 9x, just to see what's happening at those critical points. We know that if there is a local maximum or minimum, it's got to be at these points. So I'm going to punch in the graph real quick and I'll bring it into the notes. So we can see from that graph that we do indeed have local extrema at -3 and +3. In fact, it looks like on the graph have a local maximum at -3 and a local minimum at +3. But we can see also from the graph that neither of those local extrema are absolute extrema, because you can see the graph goes off to positive infinity as you move to the right, and goes off to negative infinity as you move to the left. Okay, so let's look at this next function here. F of x equals sine of x times cosine of x. Same as before, I would like to find all the critical points of this function. So this is going to test our knowledge of trigonometry a little bit. But first, if we're going to find the critical points, first thing we got to do is find the derivative. We could just go ahead and use the product rule, but I do know that sine of 2x is the same as 2 times sine of x times cosine of x. So I can see that this is really the same as 1/2 sine of 2x. And I think that would be easier to differentiate. We won't have to use the product rule. So then f prime of x, you got 1/2. Then when you differentiate the sine function, you get cosine. Leave the inside function alone, 2x. But then you got to multiply times the derivative of the inside function, which is 2. So you end up with cosine of 2x as your derivative. Now, we have to consider the two kinds of critical points. We want to find the points where f prime of x equals 0. So we're going to have to set cosine of 2x equal to 0 and solve for x. Okay, so I have to use my knowledge of trigonometry here. I don't really have so much of an algebraic procedure that I can do to just isolate x and solve for it. I just kind of have to think in terms of what input values make cosine equal to 0. Well, when I think about the unit circle, cosine is equal to 0 at the position of pi over 2, so kind of like 90 degrees, and also the angle that points straight down, 270 degrees, or 3 pi over 2. But then, cosine's a periodic function, so if you add 2 pi to either of those angles, you end up getting the same values of cosine. So we actually have infinitely many critical points here. So turns out, when you think about it, in terms of the unit circle, this is going to happen exactly when 2 times x, the input of the cosine, is equal to pi over 2. And then starting from pi over 2, you can add any multiple of pi that you like. So plus n pi, where here n is an integer. So I can indicate that with this symbol here. That reads n as an integer. And then if I want to isolate x, I can now divide by 2. And so I'd get x has got to be pi over 4 plus n times pi over 2, where n is any integer. Okay, so I think I've got all the places where the derivative is equal to 0 there, infinitely many of them. And the second thing I got to think about are points where f prime of x is undefined or just does not exist. And when I look at the derivative cosine of 2x, I know that the domain of the cosine function is all real numbers, so we just don't have any of those kind of critical points where the derivative is undefined. So all of our critical points are just the ones that we got from step 1. It's all the points of the form pi over 4 plus n times pi over 2, where n is an integer. If I looked at a graph, I should be able to see that. Let's do that real quick. I'll generate a graph and paste it right here into the notes to see what we got. So yeah, looking at that graph, you can definitely see that at pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, all those places, the tangent line's going horizontal at those places. In other words, f prime's equal to 0 at those places, and so those are critical points. So it seems like our algebra was correct. Let's do another. Okay, for this example, we have the function f of x equals x squared times the square root of x plus 5, and we want to find all the critical points. Before I start thinking about finding the critical points, I should think about what is the domain of the function. And just a quick look at that function, you realize that x has to be bigger than or equal to -5 in order for that function to be a real number. Or if you want to think of the domain as being -5 to infinity. So if we're thinking about critical points are points interior to this, right? So I would never consider -5 as a critical point, or anything less than -5, the function's not even defined. So if I happen to find some candidate critical values that are outside of that domain or on the boundary of it, I would just discard them. Okay, so let's find those critical points. First thing we got to do is calculate the derivative. So f prime of x, I'm going to use the product rule. I have 2x squared of x plus 5. And then when I differentiate the square root of x plus 5, I get 1 over 2 squared of x plus 5. So this will be x squared over 2 square root of x plus 5. Okay, now I got to find the critical points. And just parenthetically, I'm going to note that the critical points have to be in the interval from -5 to infinity, the endpoints not included, where the derivative is equal to 0. So I just set 2x squared of x plus 5 plus x squared over 2 square root of x plus 5. Set that equal to 0. You know, situation like this, I think I'll multiply everything by the denominator of that fraction just to clear fractions. So if I multiplied everything by 2 times the square root of x plus 5, I'd get 4x times x plus 5 plus x squared equals 0. And from there, I see I've got like 4x squared plus x squared, that'd be 5x squared, plus 4x times 5, that'd be 20x, equals 0. And then I could divide through by 5 and factor out an x. So I'd have something like this. So just write it like this, 5x times x plus 4 has to equal 0. So from there, setting the two factors 5x and x plus 4 equal to 0 individually, I would see that x has to be 0 or -4 for those critical points that make the derivative equal to 0. And the second bit, I got to do the critical points again in the open interval -5 to infinity, where the derivative is undefined. And up here in our expression for the derivative, I just think about where would that be undefined, right? Well, the first term in that sum would only be undefined for x's less than -5, but we're excluding those. We're only consider x's greater than -5. And with that fraction, the only way that's going to be undefined, well, you could get 0 in the denominator if x is equal to -5, but that's the endpoint that we're excluding. And then, of course, the radical you'd have a negative inside the radical when x is less than -5, but we're also excluding those points. So here we don't get any of those type of points in the interior of our domain where the derivative is undefined. So the total set of critical values here, the critical points, just consist of 0 and -4. So something interesting might be happening at the graph at those 2 points. And we could certainly go get a graph and do that. I'll go make a graph and then paste it into the notes here and we'll look at it. Okay, and so there's the graph. And you can certainly see something's happening here at -4. In fact, I can see that we've got a local maximum at -4. And I can also see that something's going on here at 0 because the tangent line goes horizontal there. At 0, I can actually see that we got an absolute minimum. You also have an absolute minimum here at -5, and we knew that that sort of thing can happen at an endpoint. And here we got a local min whenever x is equal to -4. But yeah, these critical points are picking up some of these places, right? The critical points don't account for what happens at the endpoints of the domain, but it'll pick up all these places where you have hilltops and valley bottoms on the graph. Okay, so hopefully that gives you a sense of how you go about finding the critical points. The main thing I'm hoping that you get out of this is that, 1, calculate the derivative, and then you have to consider the 2 separate kinds of critical points. There's the first kind of critical point where the derivative is equal to 0, and the second kind of critical point where the derivative is undefined. And I found that students often neglect the second kind of critical point. You always have to check it though. Where is the derivative undefined? Because that can give you more critical points. Okay, the next question I want to consider is, how do I know when a function even has an absolute minimum or maximum on its domain? So I want to consider several different scenarios and try to see if we can get some clues about that sort of question. So consider that first graph there on the left. We've got f of x equals x cubed on its entire natural domain of -infinity to +infinity. Well, you can see that there's no maximum, like there's no absolute min or maximum, right? Because it goes up to infinity on the right-hand side and goes down to -infinity on the left-hand side. So you might say to yourself, well, how about if I just restrict like what if it was a smaller domain? Like, for example, what if I restricted it to same function, but just on the open interval from -1 to +1. It looks like maybe you could say you've got a maximum, say at this point, but actually, no. That point, since there's a little circle there, is not part of the graph of the function. So it's not, I can't say that that value where that dot is a maximum of the function because it's not a value that the function takes on. And so, same thing on the left-hand side, you might think that's a minimum, but no. So whenever we have open intervals, it causes problems trying to get a maximum because the function gets close to that point but never quite makes it there, so we can't say that that point at the end is a maximum or a minimum. But when you look at the last situation, if we restrict our x cubed to the closed interval -1 to +1, then we see that we really do get an absolute maximum there on the right-hand side, and we also get an absolute minimum on the left-hand endpoint. As long as the function's defined at an endpoint, you might get a maximum or a minimum there. But what's really important here is that the function x cubed, once we got it restricted to a nice closed interval, we can see that it has an absolute maximum or minimum. But what if we have some weird function that's not even continuous? Like look at that example on the bottom left there. I don't want to try to write down the formula for that function, although I could. Just be a little yucky. But just that function represented by that graph, well, I can see that a couple points that might be candidates for being a maximum or a minimum. So it is a function that's defined on this closed interval, -2 to 2. It's defined at every point in the middle. Even where those breaks are, it's defined. But, the candidate for an absolute minimum would be there. But no, it's not for the same reason as above. The function never really quite makes it to that point, so I can't say that that point is a minimum for that function. And same thing over here. You might think, hey, that point looks like it could be an absolute maximum. But no, for the same reason. The function just doesn't quite make it there. So it's not the highest point on the graph in that neighborhood. And the example that's on the lower right, it's a function. I'm going to add 1 point to the graph so that the function is defined on that entire interval from -2 to +2. But I can see that that function doesn't have any absolute maximum or minimum because it clearly goes up to infinity on the right-hand side over there, and then it goes down to negative infinity on the left-hand side of 0. So it's not enough just to say, hey, I've got a function restricted to a closed interval. You can see maybe where I'm going with this. What critical property do we need the function to have so that we'll be sure that it has a maximum and a minimum on that closed interval? Well, those last two examples lack the property of continuity. The one on the left bottom has jump discontinuities, and the one on the lower right has an asymptote discontinuity. So, well, here's the answer that I'm sort of driving toward through example. The extreme value theorem. It tells you so long as your function is continuous on the closed interval a to b, it's definitely going to have an absolute maximum and an absolute minimum on that interval somewhere. We really like to have ourselves a nice continuous function on a closed interval because we know there is some maximum, there's some minimum, and then maybe we have some hope of finding it. So here's what we know so far. If we take all the things that we talked about. So we just learned that if you got a continuous function on a to b, then the function definitely has one of those absolute minimums and it has an absolute maximum somewhere at a point on the interval a to b. And then we also know that anytime a function has an extremum, local or absolute, then it has to happen at a couple of different places. So it's either at an endpoint. So if f has an absolute extremum at x equals c, then I know c is an endpoint of ab, or I know c is a critical point somewhere in the open interval from a to b. So what we see from, if you put 1 and 2 together, we actually have a procedure that always works for finding the absolute extreme values on a closed interval. Okay, the first thing you do is you find all the critical points of the function in the open interval a to b. So those are just the places, remember, where the derivative is either equal to 0 or the derivative does not exist. And then you've got the endpoints for step number 2. And then the third step's really easy. What you get from the first two steps here, 1 and 2, you got your candidates where the extrema occur. And then the third step is just to test each of your candidates. So take each of your candidates and plug them into the function, and then just see what's the biggest value and what's the smallest value. And then that's the answer. So the third step is just test the candidates in the function f. So let's see a few examples of using this procedure. In this first example of finding the absolute extrema on a closed interval, got the function f of x equals x to the fourth minus 4x cubed plus 4x squared, and the interval that we're looking at is -1 to 3. So I got to first find those candidates. And 2 of the candidates are very easy. It's just the endpoints of the interval. Let's find the critical points in the open interval -1 to 3. Well, first thing I got to do is get the derivative. So the derivative is 4x cubed minus 12x squared plus 8x. And then I'm just going to make a little note here. F prime is defined for all x. So I don't need to worry about any critical values where the derivative is undefined. I only need to figure out where the derivative is equal to 0. Okay, so setting 4x cubed minus 12x squared plus 8x equals to 0, I see that I could factor a 4x out, and that'd leave me with x squared minus 3x plus 2. And then I further noticed that quantity in the parentheses there, I can factor it. So I could factor this as 4x times x minus 1 times x minus 2. So by taking each of those 3 factors and separately setting them equal to 0 and solving for x, I arrive at x has to be 0, 1, or 2. And then I'm just going to point out that all of these points are interior. Well, let's just say in. These are all in the interval from -1 to 3, so I'm going to keep all of them. If I had found a critical point that was not in my interval, I would discard it. In this particular case, though, I'm going to keep all of those values that I just found. Okay, and like I said, we don't have any places where the derivative is undefined. So then our candidates, we got our critical points, 0, 1, and 2. And we also got to include our endpoints, -1 and 3. And so then the next step of this procedure is to just plug all those into the function. So literally all I'm going to do here is I'm going to plug in, I'm going to do f of 0, f of 1, f of 2, f of negative 1, f of 3. I'm just going to see what I get when I plug those into the function. Now don't make the mistake of plugging these into the derivative. I'm plugging them into the original function that we had at the very beginning. So x to the 4th minus 4x cubed plus 4x squared. Okay, after plugging in all of the values, I got f of 0 equals 0, f of 1 equals 1, f of 2 equals 0, f of negative 1 equals 9, and f of 3 equals 9. What's the biggest value that you see? That's your maximum. Well, I see that you get a maximum value of 9, and it occurs at two different x values. And I also see that the smallest value of 0 occurs at two different x values. So from what I see here, this tells me that f has an absolute minimum of 0 at x equals 0 and x equals 2. And I also see that f has an absolute maximum of 9 at x equals negative 1 and x equals 3. We should expect to see our results that we found algebraically verified if we look at a graph. So I'm going to go graph the function and compare it to our answer here real quick. So bringing in the graph, we really do see that we have an absolute minimum at x equals 0 and at x equals 2. Those are those low points on the graph where the red dots are. Bear in mind, this graph does contain a little bit about what happens beyond negative 1 and 3, but we're only looking at what happens strictly between negative 1 and 3. And we also see that at negative 1 and at 3, that appears to be where the high point on the graph is, right? And you can see that the height there is 9, like we thought it was. F of 1 was, in fact, you did have a local minimum there, but it wasn't an absolute minimum. So our procedure worked perfectly here. And we also see that the absolute minimum doesn't have to just happen at one place. You can get the absolute minimum happening at multiple places. And same thing with the absolute maximum. Let's try another one using this procedure. In this example, we got f of x equals x divided by the quantity x squared plus 3 squared, and our interval is 0 to 2. And same as before, we want to find the absolute minimum and absolute maximum of this function on that interval. So we're going to find our critical points that happen in 0 to 2. They have to be interior to that interval. Well, to do that, we'll find the derivative first. So f prime of x. Sometimes I don't really like to use the quotient rule because, I don't know, it's a little messy. So what I could do instead is to take the original function and write it as x times x squared plus 3 to the negative 2. So instead of using the quotient rule to do the derivative, I'll do the product rule instead, which I always find a little bit easier. So now f prime of x, derivative of the first term is just 1, so I'd get x squared plus 3 to the negative 2 plus, and then I leave the x alone, and then it becomes negative 2 times x squared plus 3 to the negative 3, so I'm using the power rule there. Then I got to multiply times the derivative of the inside function, that's 2x. Okay, so now I'm done differentiating, but I think I'm going to put it back in fractional form. So this would be 1 over x squared plus 3 squared, and then looks like I'm going to have minus 4x squared divided by x squared plus 3 to the third, like that. And now we have to find critical points. Critical points are just places where the derivative might be undefined. I just want to make a note here that f prime exists for all x, because the only way that expression is going to be undefined is if you're dividing by 0, but notice that x squared plus 3 is always greater than 0. In fact, it's always greater than or equal to 3. So you can't get a 0 in the denominator, and so we don't have any problems with that derivative. So all we got to do, we just got to find the places, the x's, where f prime of x is equal to 0. And so setting that derivative equal to 0, I'm just going to multiply everything by x squared plus 3 to the third power to clear fractions. And if I do that, I'm going to end up with x squared plus 3 minus 4x squared equals 0. So here I just multiplied by x squared plus 3 to the third power. And then that becomes, looks like, negative 3x squared plus 3 equals 0. And if I subtract 3 from both sides, divide by negative 3, I end up with x equals plus or minus 1. So those are my critical points. Now, are both of those points in the interval that I'm interested in? No, actually. The only one that I care about is positive 1, so I'm going to discard. So I guess I should say, maybe say it like this. Critical points in the interval 0 to 2, the only one I would keep is 1. Okay, so I got one critical point that I got to consider. And then I've got the two endpoints. And so my candidates are 1 and then 0 and 2. The 1 is your critical point, and then 0 and 2 are your endpoints. And so then all I got to do is just plug those three numbers into my function. So I got to look at f of 1, f of 0, and f of 2. So remember, the idea is you're going to plug those numbers into f of x equals, what was our function? X over quantity x squared plus 3 squared. Now numerically, which of these is the biggest? I think 1/16 would be your maximum. And clearly 0 would be minimal. I know it makes you feel a little weird when you get such weird numbers for your answers, but I guess the truth is, the numbers don't always work out to be super nice. I would say I've got an absolute minimum of 0 at x equals 0, and I got an absolute maximum of 1/16 at x equals 1. Now I'm really curious to see if the graph bears out our algebraic results, so let's find out real quick. So yeah, examining the graph, I can see that there's a maximum occurring at x equals 1, and sure enough, if you plug 1/16 into a calculator, you'll see that 1/16 is equal to 0.0625, and so there's where you're having your maximum at 1, and then you see you're having a minimum of 0 at 0. Remember, our interval here that we're considering is 0 to 2, so we're not considering anything that happens beyond 0 to 2. So yeah, the graph confirms our answer. So we're happy about that. Okay, so I think I've given you enough examples to sort of get you started on doing this. Typically, the most challenging step of these finding absolute extrema of functions is finding the critical points. In particular, the part where you have to set the derivative equal to 0 and solve for x. Sometimes that'll put your algebraic skills to the test, but it is something you definitely want to practice. I would ask you to always try to do the algebra by hand instead of going straight to some sort of calculator to solve that for you, because whenever you're taking exams, you may be asked to do it without the aid of a calculator. And so developing your algebraic skills will be important, not just for this class, but as you move forward as well. Okay, I'll stop there and talk to you next time. Bye now.